So this Gaussian algorithm, we're not learning it because we're necessarily going to use this every time we transform a matrix into row echelon form. It's kind of tedious to follow this exactly, right? Using our human intuition is a little bit easier than following the algorithm exactly. But the utility of the algorithm means why the algorithm is useful is that because there is an algorithm, we can teach a computer how to do the Gaussian elimination steps. We can tell a computer to do the Gaussian algorithm, and it can find a matrix in row echelon form. And so in this class, and many times that's exactly what we'll do, because as you may have noticed, it's quite tedious to get a matrix into row echelon form or reduced row echelon form, and we're dealing with relatively small matrices. As our matrices get larger, this is going to get more tedious, more difficult. So there are many calculators out there that will allow you to convert a matrix to row echelon form or to reduced row echelon form. I'm going to use Python, which is a computer programming language, together with a library called SymPy. And it's a good introduction to more advanced techniques using linear algebra in computers, because a lot of real-life applications of linear algebra use Python. But we'll just be using it in a very simple way. So first, I'm going to import my library. So the library is called SymPy. This is symbolic Python. It's a library that allows Python to compute symbolic math. Okay, so from SymPy, import star. That means from this library, import, and then the star means everything. Import everything. Okay, and I'll click the little play button, and it will run, and I have a little check mark that says it's done. Okay, and now I'm going to add another code cell. And now that that's loaded up, I can tell the computer to row reduce a matrix. So let's take the same example we just looked at. I'm going to call this matrix A. First, I need to tell the computer what the matrix is. Okay, so A is equal to this matrix. So to define the matrix, I'm going to put the matrix in between these square brackets. Okay, and each row I'm going to put in a different set of square brackets. So row 1 is 0, 1. Row 2 is 2, 2. And row 3 is 3, 4. Okay, so the outer set of square brackets tells me I'm dealing with a matrix, and then each inner set tells me each row of the matrix. Okay, now we could actually format this to be a little nicer looking. I just put the matrix on the next line, and then each row on the line after. And now I could see that this matrix really looks like the matrix that I want, right? 0, 1, 2, 2, 3, 4. Okay. So I ran it, it works. Now, we want to do something with this matrix, though. All the computer knows right now is that this is a matrix, but we want to tell it to do something with that matrix. So I'm going to type the matrix name. I've decided to call the matrix A. Dot, and I'm going to type RREF, reduced row echelon form. And then 2 parentheses. This says, take matrix A, put it in reduced row echelon form. And the parentheses here just mean that this is a function. This is something for the computer to do. Okay, so if I run that, it does it. And you get kind of this gnarly looking result. We can make it a little prettier looking if we type pprint. That stands for pretty print. It's going to print it so that it looks a little nicer. So now if I run it, it will give me the same result, but it looks a little nicer. So it gives me my the reduced row echelon form of the matrix. It also gives me some other information here, which we don't need to know right now. Okay, but this part right here on the left side, that's the reduced row echelon form of the matrix. And if we were to continue reducing this, let me just copy it again, we could see we would get the same reduced row echelon form. Okay, so I could take row 1 minus 2, row 2 is my new row 1. That would give me just very quickly 2, 0, 0, 1, 0, 0. And then multiply row 1 by 1/2. And I get 1, 0, 0, 1, 0, 0. And that is the exact, so this is now in reduced row echelon form. I got the stair-step pattern, all leading entries are 1s, 0s in all other entries of the columns with the leading ones. This is in reduced row echelon form. And it matches exactly what I get using the computer. And so for most of this class, we are going to need to put matrices into reduced row echelon form a lot. So for most of this class, we will use the computer to do the heavy lifting for us because it can use that Gaussian algorithm and the algorithm for Gauss-Jordan elimination to find the reduced row echelon form of the matrix.